In this video, we're going to take a look at the Vesper Theory, which is the idea that molecules are actually not 2D, but they're three-dimensional. And how do we figure out the three-dimensional structure from their 2D Lewis dot structure? Well, we use a theory called the Vesper Theory. And so we're going to learn about how that all works to convert 2D structures to 3D structures. So remember that molecules are not 2D, they are three-dimensional, 3D. And we use Vesper theory to predict the molecular geometry. So the geometry or the shape of the molecule, and it's actually based on the electron regions that are surrounding the central atom. And those electron regions can be lone pairs and also bonded pairs. Vesper stands for valence, shell, electron, pair, repulsion, and then, well, theory. And so what that means is the shape is determined by how the electrons surrounding the central atom actually repel each other. Remember, electrons all have a negative charge, and so if they're too close to each other, they're going to repel each other. And so the way the atoms surrounding the central atom will arrange themselves and the electrons surrounding the central atoms will arrange themselves is in a shape that minimizes repulsion. It doesn't want to feel tense or strained. So the shape that it has to have is going to minimize the repulsion of the negative charges from all those electron regions. And so you can see that over here we have a central atom, we have electron regions, and there's repulsions happening. And so these will spread out in a way that gives you the fewest, or that minimizes that repulsive force. So here's our 2D Lewis structure, and here's our 3D molecular geometry based on Vesper theory. If you have a setup that looks kind of like this, your shape will be what's called tetrahedral, and I'll show you how to figure that out in a bit. But this is the best shape to minimize repulsions. You would think that this is the best 3D shape here, where you have sort of 90 degrees between those atoms and 90 degrees between these atoms, but that actually has a lot of strain for all these bonded electrons in there. So the best way to minimize the repulsion between the bonded electrons there is to use this setup here, which is tetrahedral. So you kind of have one of the atoms pointing on top, one sort of going behind the screen there, one coming out at you in front of the screen there, and then one just sort of on the side there along the screen. So this is the better arrangement called the tetrahedral arrangement for the molecule of methane. So this is based on symmetry. Now, to draw a 3D structure, you use what's called a wedge dash projection. In a Lewis structure, you just use these solid lines like you see here. And those solid lines basically mean that your structure is on a 2D piece of paper. But the wedge dash structure lets you show you that some atoms are going sort of behind the screen, away from you. Some atoms are coming towards you, and some atoms are, well, on the screen or on the paper. So usually the wedge line, so this thick line over here, that's to represent atoms coming towards you, coming forward. The dashed line over here, that represents atoms, well, going away from you or into the screen, behind the screen. And then the solid line is, well, in the plane of the, let's say, screen, since you're watching this, or paper if you're drawing it. So this is in the plane of the paper there. And so your goal will be to take a Lewis structure, figure out what its 3D shape should be, and be able to draw that 3D shape. So to do that, we have a fancy table here that lets you figure out what the 3D structure will be based on what your Lewis structure looks like. So if you're asked to draw 3D molecules with Vesper theory, first draw the regular Lewis dot structure, then come to this table here and take a look at what your regular Lewis dot structure matches, and then you'll get the shape name and also what the shape should look like as a 3D molecule. So let's take the Lewis structure of methane again, for example, CH4. We need to find how many bonded bonds and lone pairs are on the central atom. So that's just kind of everything together. So there's essentially 1, 2, 3, 4 electron regions. So right here. And how many lone pairs are on it? Is it 0, 1, or 2? Well, there's 0. So we find ourselves over here. This is going to be a tetrahedral molecule. Tetrahedral. And we're going to put our central atom in the middle, of course. Two of the bonds will be just solid lines, H, H. And then one of the bonds will be kind of going away from us as a wedge, as a dash line. And then one of the bonds will be coming towards us as a wedge. And so that's a tetrahedral shape for methane. And actually, let me just draw this a bit more effectively. I don't like the way I did my back line there. More like this. That's better. There you go. The other one was angled too far up. Let's try this one here. So we have carbon dioxide. No, sorry, this is ozone. I thought it was a carbon in the middle. There's 3 oxygens there. And so we have how many electron regions around the central atom? We have the 1, 2, 3. So there's 3 electron regions. How many of those electron regions are lone pairs? Well, 1. So that leaves us over here with a bent structure. And so what we do is we write down the name of that structure. The shape is bent. And we put the central atom first. Put your lone pairs there. And then draw it looking bent solid lines there. So one of them's like this. And then the other one, we keep our double bond as a double bond. Like that. So it's a bent structure, and it makes sense because, and you don't have to draw these arrows in, but these are kind of pushing these ones down there, and then these ones are repelling, so they won't come right next to each other, but they'll be a little bit closer to each other than they normally would because of the lone pairs up here pushing those down. So again, you don't have to draw those arrows I just mentioned there, but that there is our Vesper structure. Now, let's try this for ammonia. So we have 4 regions. So back here, how many lone pairs? 1. So we have Trigonal Pyramid. And so we're going to have our nitrogen like this. We're going to have 1 wedge coming out at us. So that's going to be our H there. We're going to have 1 wedge going away from the screen. I shouldn't say wedge, I should say dash, because it's going away from the screen, and then 1 in the plane of the screen. And so that there is our trigonal pyramidal for ammonia. So you should be able to go and do the same exercise with the examples we did in the previous video for the Lewis structures, and actually we'll do that together here. So you can use the Vesper chart and name the Vesper chart to find the name and the shape, and the Vesper chart is basically just this thing over here. It's found in a data table for you. There are 2 questions where I give you a Vesper chart that's a bit more expanded. It has more shapes, and so you usually won't see these ones here. The ones that require more shapes, these are typically for grade 12 usually. But if you do see them in extra worksheets that you do, you can take a look at this chart here, and it kind of works the same way. So let's go ahead and do that here. Let's do the CCl4. So CCl4, we already drew the Lewis dot structure, but that would be the first thing you'd be doing. It has 4 regions, 0 lone pair, so that's also tetrahedral. So CCl4 is tetrahedral. And so we have our Cl, Cl, our wedge there, Cl, and then our dash over here, Cl. Tetrahedral. Let's take a look at water. So 4 electron regions, but it has 2 lone pairs. So that's a bent molecule as well. And so if you look at the table, so this is bent. We have O, H, H, and the 2 lone pairs are up here like that. So this is a Lewis structure over here, but this is a Vesper structure. This best represents its shape with the bent and the 2 lone pairs like this. That's the best shape to minimize repulsion there. Let's take a look at CO2. Around the central atom, carbon, there's 2 electron regions. So I know it looks like there's 4 bonds. It's really 2 double bonds. The double bonds each count as 1 region, and triple bond counts as 1 region as well. So don't think that, okay, double bond is 2 each. No, it's just 1 region each of electrons. So a region of electrons each. So really there's two electrons regions, 0 lone pairs. So we have a linear structure we're looking at. Linear. And so we have C, and we can just draw it the same way essentially that was before. It's a nice straight molecule. If you were looking at angles, essentially the angle here would be 180 degrees. And so that's how we call it a linear structure. This one here doesn't really have a central atom, so to speak. So if you were to look at the number of regions, it wouldn't quite follow that Vesper chart. But in this case, since we only have 2 elements, it really is just going to be a linear structure. This just follows sort of a it would be similar in shape to the carbon dioxide above. So it's just a linear structure, and we could actually just draw it the same way. So this here is interesting. This one here has 3 regions of electron density, so 3 electron regions, like you see here, but 0 lone pairs. So we have a trigonal planar. And so if you look at trigonal planar, it's almost like a triangle we're drawing there. So we're going to do this, this, like that, and like that. And in grade 12, you'd learn that the angle between those atoms there is 120 degrees all around. And I'm pretty sure you can already start to predict some of these. So here we have 0, we have 2 regions of electron density with 0 lone pairs. So we're back to a linear. So here we have linear. And then we can just draw it the same way. And then we get to the example where we have a something beyond the chart that you have. This would be more for grade 12, but I'll show you how to use it anyways. It's roughly the same thing. It's actually found in your unit calendar. So we have our unit calendar over here. Or actually, let's go to our note. Our note for this right here, because I linked it. So right here, this is the Vesper reference chart. You'll notice we have 6 electron regions, we call that domains because it's SF6. There's 6 things around it. And they're all bonded. It's all bonded. There's no lone pairs, so it's a similar table, just a bit larger and has angles and everything. You don't need to worry about that right now. But the example there in our notes would be this one here, and we look at the molecular shape. Don't look at the electron geometry now. We look at molecular shape. The molecular shape is going to be octahedral. Octahedral, which looks essentially like this here. So two going at the back, two coming out, and then two along the plane there. So this is an octahedral shape. So octahedral. And so we have two sort of along our, just going to erase that grade 12 part so I could write. Two along the top there, or one along the top, I should say, in the plane, one along the bottom in the plane, then two coming out at us as a wedge, and then two going behind us as dashes. Again, that's more of a grade 12 shape, but if you do come across any extra practice that you can use that chart there till you find the shape. This one here, you didn't really need to actually use the chart with more shapes because we only have, if you look at a central atom, 1, 2, 3, 4, 4 regions of electron density, and there's no lone pairs. So based on that, we're dealing with a tetrahedral type of molecule. Tetrahedral type of molecule. And it depends really on how you drew it. But the idea is that you'd have, for example, P over here, double bond O in the plane here. Then you have your OH in the plane there as well. You'd have your other OH coming out of the page here. And then you'd have your other OH going into the page there with your lone pairs, of course. And that would be your molecule of H3PO4 in its Vesper shape, which is tetrahedral. So that was the Vesper lesson. You should practice doing some Lewis dot structures and trying to find the shape of some of these molecules as Lewis dot structures. If there are any, like I said, that do go beyond the shapes that are in this table here, then do make sure that you use the additional Vesper Theory table that I gave you. But for the most part, you're going to be using just that simple one. And for the simple one, you can find it in your notes. And you can also find it in our unit calendar over here under the data tables that are provided to you. So we have other data tables here. And when you go in there, you'll see the Vesper chart, and you're allowed to use that on assessments to come up with the shapes.